Okay, cool. Hi, everyone. So, last lecture, we introduced the idea of a mixed state in quantum mechanics as sort of a general framework that can include both classical probability distributions and also quantum mechanical superpositions and so on. And we saw that these states were very neatly characterized by what's called a density matrix, rho, which can be written as sum over pi, psi I, where this represents, or one thing it represents, multiple ensembles can have the same density matrix, but one ensemble it can represent is having probability of pi being each of the states psi I. Okay, and in particular, we saw how if you have some state rho AB, and there's a density matrix on HA tensor HB, then we can do what's called a partial trace over B and get a density matrix just on HA, called HA, rho A, and that sort of is a smaller thing. It involves a smaller dimension space, but it can describe any measurement done just on subsystem A. Okay. So today's lecture, we're gonna sort of use this framework that we now have to talk about a very fundamental basic question in quantum mechanics, which is what does it mean for a measurement to happen? Like when we have this sort of postulate about how measurements work, but we sort of so far treated them as just some independent like framework from the usual rules of how quantum mechanical systems evolve, just a sort of magical thing, and then a measurement happens, and you update the state in this weird way. And today we're going to try and understand as much as we can what actually goes on. Okay. And the sort of key lesson in this whole story, the key sort of most insightful comment anyone has ever made about measurement in quantum mechanics is that measurement devices, the device you're using to do the measurement, the box that gives out some little reading that says what it is, are quantum mechanical systems too. Okay, just like the thing you're measuring, at the end of the day, the universe is quantum mechanical. No matter how big a system we're talking about, some people will disagree with this, but most people would say that the whole universe is just a big quantum mechanical system. Okay. What does this mean? Well, the sort of basic conclusion is that measurement is just unitary time evolution. So ordinary, so Schrödinger equation, time evolution, some unitary gate being applied, where the system that gets measured is interacting in some way with the measuring device. So there's some unitary you measure that takes us from the sort of input state of measuring device and thing being measured to the output state where the two have interacted. This is obviously a very different formalism from the usual way we talk about measurements is just some set of projectors acting on the quantum system, and we don't talk about the measuring device at all. We'll see how it connects back to that thing in a minute. Okay. But in particular, so how might this U measure work? What does it do to different states? Well, let's say we're trying to do a measurement that measures a qubit in the 0-1 basis. Okay, so we maybe have our qubit that might be in the 0 state, and we have some measuring device, which I'm going to draw as a little scale, has 0 at one end, 1 at the other end. And initially, this is just sort of in the null state, right? It's not reading any measurement outcome. Okay, so we just have this is just some big quantum system, has lots and lots of orthogonal states. One state we're going to call, associated with this measurement device just having its meter in the middle. It doesn't know whether the state is 0 or 1 yet. Okay. Now we're going to apply U measure to this. What do people think the output state is going to be? If we start with the qubit in state 0 and we have this measuring device that's trying to work out whether the state is 0 or 1, what's it going to end up in?
0, 0.
Yeah, awesome. So the qubit is still going to be in the state 0, but the measuring device is now no longer going to be a sort of null state that doesn't know whether it's 0 or 1. Now the measuring dial will have gone to the left, and it will now say 0. Okay, great. So this thing we want to treat as large quantum system. We want to say that this is just an orthogonal state to the initial state of the measuring device. Okay. Similarly, we could apply U measure to state 1 and a null measuring device doesn't measure anything yet. And that will give a state where the measurement outcome is 1. Okay. In particular, yeah, we want to say that these two states are going to be orthogonal. So we can look at the measuring device and distinguish the two states exactly. That they're just independent orthogonal quantum states. Okay, so that's obviously great, but what about if the state of the qubit is some superposition of 0 and 1? Okay. Well, you might say, okay, I don't know what's going on here. That's more complicated. But actually, just because this is a unitary matrix and unitaries are linear, then we know exactly what will happen to this state, right? So we apply U measure. We have psi, and we have the measuring device in the null startup state. Okay, and this is just a linear combination of this input and this input. So this just gets mapped. Well, the component that is 0 tenths of the null state goes to alpha 0 measuring device in the 0 state, and the component that has the qubit in the 1 state, the amplitude for that goes to 1 measuring device in the 1 state. Okay. So what's happened here? Right, we've ended up in some state where the measuring device is entangled with state of the qubit. Okay, you've got some component that has the measuring device reading 0 and the qubit being in state 0, and we have a component where the measuring device is in state 1 and the qubit's reading 1. Okay. Now we could say, okay, so what's the state of the qubit at this point? So previously, with the formalism we had, we wouldn't have been able to answer that question at all, because we just, if we had an entangled state, if we had something that wasn't a product state, then we just weren't allowed to talk about the state of one of the two systems at all on its own. But now we can talk about mixed states. We can do so. So the reduced state rho qubit is equal to the trace over m of rho qm, where this is just equal to the trace over m of u measure psi just this pure state where the measurement device has got entangled with the state of the qubit. Okay. We can do this partial trace explicitly, right? So we have two terms in the ket and we have two terms in the bra. And when we do the partial trace over the measuring system, because these two states are orthogonal, then the off-diagonal terms get cancelled. And the only things we're left with, check this for yourself if it's not obvious, is the on-diagonal terms, where either both the bra and the ket are in the 0 state, or both the bra and ket are in the 1 state. Okay. So you notice that now the state of the qubit is now mixed. Rather than being a coherent superposition of 0 and 1, it's just a mixed state containing both a mixture of 0 and 1. And this is this phenomenon has a name. It's called decoherence. So if you hear the word decoherence, sort of a bit of a fancy buzzword within physics, but all it means is that your qubit interacts with some system, which often we think of as a measuring device, and then that causes it to end up in a mixed state. Okay. So this density matrix, rho Q, is exactly the same density matrix as we get for an ensemble where the probability of being in the state 0 is modulus of alpha squared, and the probability of being in the state 1 is modulus of beta squared. This is obviously that ensemble is exactly the expected state of the qubit. Using when we use the measurement postulate to describe what happens when you do a measurement. Similarly, if we look at rho m, that is equal to the reduced density matrix of the measurement device. It's equal to probability alpha squared, the measurement device, being in the 0 state, the registering 0, and a probability of beta squared of the measuring device registering 1. Right. Again, that's exactly the same as we found with the measurement postulate, right? The probability of the measurement outcome being 0 is alpha squared. Measurement outcome being 1 is beta squared. It's important to emphasize, if you were feeling really optimistic, you might think at this point we've sort of derived the measurement postulate. That is definitely not right. Anyone know the reason why that's not? We can't claim we've now derived the measurement postulate if we've got the right probabilities coming out of these reduced density matrices and stuff.
You can't get things like wave function collapse.
Yeah, so, but we have a probability of alpha squared of, you can check the correlation as well. And if the, yeah, I would say the real reason, I agree that's a good answer basically. But the real reason is that we needed the measurement postulate to argue that sort of density matrices made sense at all. Right, to argue that physical observables depended only on the density matrix and not on the full ensemble. Right, you have different ensembles with the same density matrix, but they're really the same. We needed the measurement postulate to do that. Okay, so this isn't a derivation, but it it is nonetheless it's a useful hint that this is the sensible way to think about how a measurement happens in practice when you take into account that the measuring device is quantum mechanical.
Can I ask a question?
Yep.
So for the measuring device, do you need it to have some knowledge about what the quantum states are? Like if you're trying to measure a particular property, like when you have to pick a particular type of measuring apparatus that would have a particular type of basis so it could measure.
Yeah, definitely. So you need your measuring device to have a set of orthogonal states that correspond to different measurement outcomes. And the big thing you need is you need to set up your U measure so that for each measured state in your the basis you're measuring, then it evolves the, say, 0 state in this null measuring device state to 0 and measuring devices measured 0. So that's two things that you need to have happen. But this is the right formalism to describe what's actually happening when you're actually doing a measurement. So anytime you physically manage to measure something, then that's basically what you're doing. Okay. Yeah. And for sort of simple measuring devices, if your measurement device is just like a photon or something like that's simple enough to really deal with quantum mechanically and not just lose all control over it, then you can literally see that this is what's happening when you do the measurement, and you can undo the measurement and stuff like that. You can just reverse this unitary process, and then no measurement has happened, no collapse of the wave function has happened. So really the thing that happens in a measurement is at least before we start talking about conscious observers and us looking in the measurement device, which we'll do in a bit, then literally all that's happening in a measurement is you're having some unitary interaction with the measurement device, and it's causing the two to become entangled. Okay, and in particular, You can explain all the famous mysterious consequences of doing a measurement. Just with a unitary evolution, so without using the actual measurement postulate at all. So, you know, something like we haven't talked about it that much this class, but something like the double slit experiment, right, which is this famous thing where when you measure which slit the particle goes through, then it destroys the coherent pattern. It changes the outcome of where the particle ends up just by doing a measurement. Then you can explain it just with unitary evolution. Okay, so we're not going to do that example because we rather think about qubits. But we'll do let's do the example going back to the very first lecture of you have a qubit, starts in state 0. Then we measure it in the plus minus basis. And finally, measure in the 0, 1 basis. Okay, so this is the thing we saw with the polarized light, right? You had light that was sort of vertically polarized, say, and if you just directly had a horizontally polarizing filter there, then no light gets through. But if you in between have a polarizing filter at 45 degrees, that's the measurement in the plus minus basis, then some light does get through. There's some probability of the photon getting measured and then ending up in the 1 state. Okay, so let's see how that works just by using unitary quantum mechanics. So the starting state of the system is we have the qubit in state 0. We have our first measuring device, which is going to measure either plus or minus. It's in the null state. And we have our second measuring device. It's going to measure in the 0, 1 basis. That's also in the null state. Okay. And this state 0 is, of course, equal to 1 over square root 2 plus state plus minus state. Okay. So then we can do the first measurement, see what happens to the state. Well, the plus state goes to plus state with measuring device in the plus state. The minus state goes to minus state plus measuring device in the minus state. And this second measuring device hasn't got used yet, so that's just sitting still in this null state where it doesn't have a measurement outcome registered yet. Okay. So that's the first step. And now we write plus, it's 1 over square root 2, 0 plus 1. Plus or minus is 1 over square root 2, 0 plus or minus 1. And we do the second measurement. Okay, so now get an extra factor of 1 over square root 2 at the front. So now the plus state, so we have 0 is 0 plus 1, but 0 goes to 0 with the second measuring device in 0. So we have 0 plus, and then the second measuring device in 0. And then we have the term from the 1 plus, right? So this goes to 1 plus second measuring device in the 1 state. And then we get the contributions from the minus state. So that gives us 0, minus, second measuring device in the 0 state. And finally, we have, we have a minus sign because this came from the minus state. 1, first measuring device in the minus state. Second measuring device in the plus state. Okay, so we just did all of that with ordinary quantum mechanics, ordinary unitary quantum mechanics. But now if we look at the reduced state, row M2, that's the second measuring device. So all these 4 states are all orthogonal. They got just on the first 2 qubits. Means when we do, first qubit, the qubit in the first measuring device, when we do a partial trace over them, we just get the answer of a half times the measuring device being in the 0 state plus a half the measuring device being in the 1 state. Okay. So we're just as likely to have measuring device register 0 or 1. Okay, so exactly the result we found way back in the very first lecture of the course, but there we did it using measurement postulate. This time we've just done it with ordinary quantum mechanics, and then at the very end we've taken a reduced density matrix, which is sort of using some input from the measurement postulate. But certainly the first measurement we treated entirely as just a unitary process. Haven't used the measurement postulate at all. In contrast, if there's no first measurement, then we just have 0 measuring device in null state goes to 0 measuring device in the 0 state. Row M2 is just a pure state with the measuring device in the 0 state. Measuring device measuring 0. Okay. So this is the sort of paradoxical, measuring device influencing the outcomes of experiments, but we've done it just by describing this first measurement that changed the outcome of the later experiment just by using an ordinary unitary evolution.
Do we know anything about the state of the measuring device? Like, because it has to be represented by a number of qubits, but I imagine it can't be like a 1 qubit state, because then it could be represented as 0s and 1s.
Yeah, so, well, it could be a 1 qubit state. I mean, it depends. If you want this null sort of initialized state to be different from either of your 2 measurement states, then it can't just be a qubit because you need to have at least 3 orthogonal states. But you could say that the 0 state represents both no measurement has happened and a measurement happened and the answer was 0, right? And the 1 state represents a measurement happened and the answer was 1. And in that case, a single qubit can do the measurement. Otherwise, you need it to be at least a qubit because you need at least the 3 states of like no measurement done yet, measurement of 0, and measurement of 1. In general, of course, if this is actually some little like dial thing that goes to left or right, then it's like, I don't know, 10 to the 20 something qubits. So it's absolutely huge. But yeah, so in practice, they tend to be very big, but there's no reason they need to be. A single qubit can measure a single qubit.
Okay, thanks.
Is that clear? Awesome. Okay, so seemingly a lot of the stuff involving measurements, a lot of how everything works, we can understand, we can do just using ordinary unitary quantum mechanics. However, we still have a big problem, which is at some point, someone, maybe it's me, maybe it's you, maybe it's someone else, is going to look at the measuring device. Right? And we know from experiment that they always just see a single outcome. Okay, well, if we believe everything is just quantum mechanics, then that must mean that not only the measuring device, but also we as sort of conscious humans or whatever are quantum systems too. Okay? We can try to describe the process of us looking at the measurement device by some unitary you look that some unitary you look where we interact with the measurement device. Okay. Now there's a question of whether this is going to make any sense, but we can at least try to do it and see where it goes. So in particular, let's say the qubit was originally in 0 and the measurement device then registers 0. And there's me. I'm just in some state that I'm representing by this neutral face. And I'm going to assume, for simplicity of diagrams, that I bet I would see 0 on the measurement device. Okay? So you look is going to evolve this state. What's it going to take it to? Well, it doesn't do anything to the qubit. It just interacts me and the measurement device. And the measuring device is in 0. So I bet I would see 0. So that is going to result in me being in a happy state where I won my bet. Right? What about if we have the qubit in 1 and hence the measuring device also in 1? Well, then presumably I'm going to see that the measuring device is in the state 1 and I'm going to be sad because I lost my bet. Okay. So again, we can just consider what happens if originally the qubit was in a superposition of 0 and 1, right? So then after doing the measurement, it's now entangled with the measuring device. So what's going to happen to this state? Again, we just use linearity, right? We just use the fact that we know that the evolution is described by unitary matrices, and unitary matrices are a linear map. So this has to go to alpha 0, 0, me. Whoops. Let me get my faces right. I'm going to have a happy face if I see 0. Me. So there's superposition of qubit in state 0, measurement device reading 0, and me being happy because I saw 0, plus some beta of measuring device being in state 1, and me being sad because I lost my bet. So if we believe that the interaction you look is really just some unitary matrix, then what it automatically implies is that in general, I will become entangled with the measuring device and the qubit. Another way of saying this, an equivalent way, is that my state, whether I'm happy, sad, what thoughts I'm having, that sort of thing, is different depending on the state of the measuring device. Okay. So what does this mean about what I actually experience, right? We have some formalism where we have a quantum state that has me being happy and the measuring device being 0, plus me being sad and the measuring device being 1. What does this mean about what I actually experience? The answer is that it's just not clear, right? We need to somehow connect this mathematical formalism to the actual experience of someone, of us, so we can compare it to predictions. And this needs an extra rule. We need more, if we just at this point knew about the rules for time evolution, we knew about like unitary evolution, wouldn't be enough to connect this state where there's us entangled with some measuring device to an actual experience that we have, right? And that rule obviously is the measurement postulate. And all the measurement postulate says is that when we end up in a state like this, where our experience is, depends on the states of other stuff, you have a coherent superposition of the different things, is that in practice, the probability that I actually experience a happy face and happy thoughts and so on is given by the modulus of alpha squared. and the probability that I actually experience a sad face is given by modulus of beta squared. Okay. So this is the sort of shut up and calculate interpretation. We just say, of quantum mechanics, we just say, okay, we have this mathematical formalism. We need to connect it to what we actually experience. That's going to need more rules than we have already. And the rule that connects it to our experience is just this thing. Okay. Of course, a very reasonable question is to ask what the hell is really going on. And this is something that can't be answered with experiment, because fundamentally, any experiment will just tell you that this measurement postulate rule works. So it's sort of outside the bounds of physics, but we can sort of comment on it anyway without giving a definitive answer. Really, there's two main interpretations. How we should think literally, what's sort of literally happening that gives this measurement postulate. The first one is the many worlds, or Everett's interpretation. And this basically says wave function, that the wave function has a sort of part where I'm happy and a part where I'm sad. So both happen. Okay, and I just experience one of them. Just take the most literal possible interpretation of this wave function. And you say both happen. You can call them like separate parallel universes or whatever. But all that's really happening is that there's some conscious observer who's experiencing both outcomes. But I'm only experiencing one because I'm just the one that I happen to experience. If I experience it was the part of the wave function experience the other one, then I'd be having a different experience. You can't talk about the two of them at the same time, right? The happy face part of the wave function, the sad face part of the wave function don't interact with one another. Of course, this interpretation has its problems, as both do. In this case, the big problem is trying to understand why you get this specific rule of probability of me being happy being modulus alpha squared, right? Why not sort of all possibilities are equally likely that I experience in them if they all happen? You can argue that all possibilities being equally likely doesn't really make sense as a rule. And in fact, you can argue that the rule that does happen, the empirical rule for what we do observe, measurement postulate is sort of the only consistent rule you can use, satisfying sort of vaguely reasonable properties. But you can't really derive the measurement postulate from scratch. No fundamental derivation measurement postulate. You always need to put in some sort of like self-consistency condition or something like that that lets you argue it has to be the answer. Okay, so that's sort of one camp. The other camp appears in a lot of interpretations, Copenhagen, consistent histories, Cubism, quantum Bayesianism. Don't worry too much about the details, distinctions of all these things. They all roughly take the attitude that no, that's completely the wrong way to think about it. You're being far too literal, you're being far too classical, and thinking of this wave function as just like a physical object that has different pieces that are each describing different realities. And we shouldn't think of the wave function as sort of a physical thing. Instead, it describes an observer's knowledge about the world. So sure, from the point of view of an observer over on Alpha Centauri, then if I do a measurement here on Earth, then no wave function collapse happens. And it's just unitary evolution where I've become entangled with the thing I measured. But that's just telling us that the observer over on Alpha Centauri doesn't know about the outcome of the measurement. They just have less knowledge than me. In particular, the fact that sort of quantum wave functions are a pretty natural generalization of sort of classical probability theory. Density matrices in particular are sort of natural generalization of classical probabilities to make things non-commutative. It's definitely some evidence of this being a sort of sensible philosophical position to take. But it does, just like many worlds, it has its problems. And in this case, the real problem is if the wave function isn't the physical thing that really exists, then what is the physical thing that exists, right? You need something else to like actually be the real thing. Because fundamentally, we need some notion of a physical reality. Maybe it's not the traditional one we've had, but there needs to be something. Otherwise, how can we have thinking observers? How can you or I be like actually experiencing thoughts if if everything is just the knowledge of the observer? The something needs to describe the observer actually existing to be having the wave function describing its state of knowledge. Okay. Any questions on everything so far, by the way?
I had maybe one thing that I was just kind of thinking about it. It seems maybe almost redundant to consider this measurement apparatus and the person. You know, it seems like the effect of including both of them is identical. You know, is it reasonable or at all? I mean, I'm sure there's some quantum phenomena where you don't even need like an actual piece of equipment to observe it directly. But I guess in general, couldn't you just kind of couple the measurement thing and the person into the same, you know, state?
Yeah. So that's a great question and ties very nicely with what I'm about to talk about. So certainly, you know, if a photon hits my eye or doesn't, then that like pretty directly gets measured by me, right? It's hard to distinguish. Like technically it gets measured by my eye and then it goes along the optic nerve and then finally my brain knows about it. And that's when the like thoughts and stuff will be different. So yeah, fundamentally, you know, you can just have, it's reasonable to say you can just have the observer directly do the measurement. I wanted to distinguish the two because I want to be able to talk about measurement devices that aren't conscious observers and distinguish them from ones that are. Because if the measurement device isn't conscious, then you don't really have to worry about what the measurement device experiences. So yeah, that's a great question. It very nicely ties into what I wanted to say next, which is that there are two common claims people make about quantum mechanics. They're sort of contradictory. They're arguing against each other. The first is this idea that quantum mechanics and the measurement postulate and things like the two-slit experiment and the fact that measuring the qubit in the plus-minus basis means that later you might measure it in the one state, shows that we live in what's sometimes called a participatory universe, right? That our conscious experience is fundamentally shaping how the universe evolves. And without us there, it would just evolve differently. Basically, I would say that this claim is wrong. There's some truth to it, but it's mostly wrong. And the counter to it that people often make is, no, you're not understanding this at all. Measurements have nothing to do with consciousness or conscious observers. An observer, someone doing the measurement, or yeah, let me rewrite this. A measurement can be done by, say, a computer, even if we don't think the computer's conscious, can be done by some little device. Or it can even be done by just like a photon or something like that interacting with the quantum system. So that so this attitude too is that don't be silly. Consciousness has absolutely nothing to do with quantum mechanics. That's a load of like bullshit, woo, blah blah blah. And measurement is just a fancy term we attach to some quantum system, complicated quantum system that interacts with the quantum system we care about. And this, I think, is mostly right, but still a bit wrong, or it still sort of conflates different things together. And I think the real problem here is an abuse of terminology. So if I was in charge of physics terminology, which I'm not, so don't go telling people that this is like the right use of terminology. There's a question in the chat that I didn't see until now, but I will respond to that in a minute. So if I was in charge of physics terminology, then I would distinguish two different things, call one of them a measurement and one an observation. Okay. So by a measurement, I would just mean a unitary interaction with a measurement device that causes decoherence. And this, of course, has nothing to do with consciousness, right? That measuring device can be as simple as a photon. Really, anytime you have any interaction at all with your quantum system, this is liable to happen. You're liable to get decoherence. You're liable to get measurement happening. But it's the thing that's responsible for sort of all the physical consequences of the measurement having happened. Okay, at least for someone who never looks at the outcome of the measurement, all the consequences of the measurement having happened are described just by this unitary process of interaction with the measurement device. What I would call an observation is when conscious observer learns the outcome of a measurement So this could be because they look at a measuring device, or as was pointed out, it could be that they just directly measure a photon or something with their eyes. And this is the part that needs the measurement postulate, right? Because this is fundamentally, if you don't have a conscious observer, you don't have anyone who's experienced, you have to be able to talk about, you never need any actual measurement postulate that needs to be used. And fundamentally, it does involve, it does have to do with consciousness because it's about what somebody experiences. But in terms of the effect on for sort of another observer who doesn't doesn't observe the measurement outcome themselves, then it's indistinguishable from the physical consequences are exactly the same as just an ordinary measurement where you just have some non-conscious measuring device like a photon or a computer or whatever it might be that is it's interacting with the system. Okay, so there was a question in the chat from Liz going back to stuff from a little while ago, which is, couldn't you construe the many worlds interpretation as a statement about knowledge too, e.g. your knowledge of which world you're in? That's certainly true, and it's certainly true that even if you subscribe to the many worlds interpretation, you can still talk about the wave function from the point of view of some observer, where they know they're in a particular branch or a particular world, and so they have a different wave function to the sort of global wave function. But the difference with the many worlds interpretation is that it takes literally the idea that a global wave function of the universe exists and has some well-defined state that's just evolving according to the Schrodinger equation, right? Sort of other interpretations would say, no, that's not something you're allowed to do. There's only the wave functions associated with different observers. In some ways, to me, this distinction feels not that big a deal. And it seems like, I don't know, the important stuff everyone agrees on, but nobody agrees with me on that. So I guess they don't. But yeah, I tend to not care too much about advocating strongly for one position or other, or whether all the things really happen or the wave function is just a state of knowledge. The more interesting thing to me is about trying to understand measurements better, is to try to understand this process of decoherence better and how it happens in practice and stuff along those lines, because there's real things you can answer there. Okay, so we got about 20 minutes left. So the last thing I want to talk about today is what's called POVM measurements. So we've sort of had our philosophy for the day. I think that's going to be basically the philosophy for the rest of the course. Going to be back onto physics from now on. But POVM measurements is a very simple idea that naturally comes out of the stuff we've been talking about until now, which is the following. If measurements are just unitary interactions of the qubit and the measuring device then why restrict the unitaries that are allowed, right? Until now, we've been assuming that these unitaries have this particularly simple form where, like, 0 goes to 0 and the measuring device being in 0 and so on. And why do we need to do that? There's no reason. So P over M measurement just says, okay, we're going to have some arbitrary unitary that interacts the state of our qubit and the state of our measuring device, which we can just assume starts in the 0 state for simplicity. Okay, and then in general, this for this arbitrary unitary gives some state where the two will generally be entangled, but we can always expand that state in the sort of computational basis of the measuring device. So we have sort of M and some state psi M. And more than that, because the overall unitary map is linear, then you can show that these psi M's have to depend linearly on the initial state psi. So they have to, so this is Q, they have to be given by K little m times psi, some linear operator Km that is called a Krauss operator. Okay. So that's just, so far we've just used the fact that the map U is some linear map. We also want to require the map U to be unitary. So that means psi 0, U dagger U, psi 0 has to be equal to 1. Okay. Well, we can write this out explicitly. So this is just equal to sum over M n psi K dagger N K M psi, and then we have an N, an M. So this is just, oops, sum over M K dagger M Km psi. The inner product of N and M just sets them equal to one another. So we want this to be equal to psi equal to 1, right? So this, if this is true for all states psi, that's equivalent to sum over M K dagger M Km being equal to the identity. Now what we do, now what we do is we imagine measuring, or maybe observing, the measurement device in the computational basis. Okay, so it's a two-step process. First, we imagine arbitrary unitary interaction, but then we say, okay, the computational basis for the measurement device is the different measurement outcomes. So the probability of getting some outcome M is just equal to let's call this state psi final. Taking psi final and projecting the measurement device into the state M. Okay, that's just our usual measurement postulate, nothing to do with POVM measurements at this point. But this is just equal, just looking at the form of this state. This kills every term except for the term with ket M here. And so this just gives us psi km dagger km psi. Okay, going to call this km dagger km a name. We're just going to call it pi m. What is pi m? Well, you can check that it's a positive operator, positive semi-definite. It's not necessarily a projector, right? If this was a projector, this would just be the ordinary measurement postulate. But now, because we've allowed an arbitrary unitary interaction, then it's just can be any positive semi-definite operator. But we can now, but we still have, when we sum over the pi m's, km dagger km, we said that had to be equal to the identity. Okay, so this is now going to be a positive operator valued measurement is just going to be defined by these operators pi m. So an ordinary measurement in this language is called a PVM, or projection valued measure. So that was just, we have some set of operators PM that are projectors and that sum to the identity. And the probability of getting some outcome M is given by the expectation of the projector, or for a mixed state, it's given by trace rho PM. Okay? So these generalized measurements or POVMs positive operator valued measure. Instead of having some set of projectors, PM, we have some set of positive operators, pi m. But they again sum up to the identity. And PM is again just given by the expectation of psi. That's what we just found above. Or for a mixed state, just by linearity, it's given by trace of rho times pi m. Okay. So you might say, what are these generalized, more general measurements let you do? Well, the big thing, so they're formalism that can describe noisy measurements. So with PVMs, with ordinary measurements, you sort of assume that the measurement outcome is like perfect and there's like no error probability or anything like that. Okay, with these POVMs, you can have something like the following. You can have for a qubit that pi 0 is projector onto 0 plus, say, a half times the projector onto 1. And then pi 1, they have to add up to the identity. So that is just going to be a half times the projector onto 1. So those add up to the identity. So in this case, if psi is the 0 state, then we find that 0, pi 0, 0 is equal to 1. Okay, so we measure 0 with probability 1. The measurement is sort of always correct. But if psi was actually in the 1 state, then because there's this noisiness, because there's some component of ket 1 bra 1 in pi 0, then we have 1, pi 0, 1 is still equal to a half, right? It's not equal to 1 anymore, but it's still equal to a half. Similarly, 1, pi 1, 1 is equal to a half. Half the time we'll measure 1, but half the time we'll still measure 0. Okay, so this measurement, doesn't perfectly distinguish the 0 state from the 1 state. Instead, it tells you, the two options for the measurement outcomes are 0 or maybe 1, or definitely 1. Okay, if you measure 1, then you know it's right. So this measurement has some probability of getting a false negative, of measuring 0 when the answer is actually 1, but it has no probability of a false positive. You can make a more general thing where there's some component of 0, 0 in this pi 1, and then you also have a probability of a false positive. Okay, so that is pretty much all I have to say. So there's a question in the chat from Juan Carlos, which says he's wondering how long should it take this evolution that does the measurement. And the answer is it can basically be anything. So we have our unitary interaction here in the most general setting that just takes this state to the interacted state. And there will be some time scale. So this will be described by a Schrodinger equation. So this is like e to the minus iht. So the time scale you need to evolve it for is the same order of magnitude as the difference between the different energies. So there's some Hamiltonian that interacts them, and the difference between energies, delta E tells you the difference. Delta E times T tells you the phase difference between different states, right? And we want to change the state significantly, so we need that to be reasonably big. So yeah, the answer is the time it takes is order 1 over the difference between energies you create between the different measurement outcomes. But in general, that can be pretty arbitrary. There's no fundamental constraint. Okay, any other questions?
I have a question about, so you said something along the lines of that the physical consequences, the physical, so you were trying to distinguish between measurements and observations, and you were saying that in some sense the measurement postulate doesn't matter for physical observations. Is that true? So what I'm thinking about is some sort of observable that's say nonlinear in the density matrix, like entanglement entropy.
So anything that's nonlinear in the density matrix is not an observable. So you can't measure the entanglement entropy. There's no physical way you can distinguish states with 0 entanglement entropy from states with non-zero entanglement entropy. We'll come to that in a couple of lectures. We're going to discuss entanglement entropy in a couple of lectures time. But yeah, fundamentally anything nonlinear can't be observed.
Aren't there experiments that try to measure entanglement in the lab?
You can do it, but you have to repeat the measurement lots and lots of times. And if you repeat the measurement lots and lots of times and different numbers of times and do different linear measurements on the lots of copies of the states, if you measure a state enough times, you can do what's called quantum state tomography, and you can actually work out what the state was, assuming it was the same each time. But you're still fundamentally doing linear measurements. It's just there are more linear measurements you can do because you have more copies. And so the density matrix of all the copies would describe everything physical you could observe using that. So the density matrix of all the copies, like, is able to know about everything. Like linear observables about it can know the exact state. Hopefully that's clear. So there's another question in the chat from Liz, which is saying, isn't there a decoherence time that is sort of associated with the measurement time? Yeah, that's exactly right. So the decoherence time is less about like you're trying to measure it and it's how long you take it to try to measure it. It's more the time scale at which just interactions with everything else around will cause the decoherence to happen, to cause the system to effectively become measured, whether you want it to or not, right? But this isn't sort of a single one-size-fits-all timescale. It's a timescale that depends on the strength of the interactions, i.e. basically, the energy gap between these different states. So a lot of the name of the game of a quantum computer, right, is if your quantum computer is being measured every billionth of a second, you can't do an interesting quantum computation with it. We sort of ignored that in the algorithm section, but when we come to error correction, we're going to be dealing with that all the time. And so your aim is to make as little of that be happening as possible, to make the decoherence time as long as possible. And different physical ways of building a quantum computer have different decoherence times. So for example, ion traps, which we'll have a guest lecture on later in the course, have a very good decoherence time so that the quantum state can last a long time without accidentally getting measured by its environment. Superconducting qubits have a less good decoherence time, but because they have other advantages, at the moment they're making more progress in making quantum computers out of superconducting qubits, but that can change. So there's no like fundamental timescale in which it happens. It just depends on the system involved, in particular, the strength of the interaction term that interacts your term and your Hamiltonian that interacts your system with stuff outside the system. Hopefully that answers your question. Okay.
Maybe I have another question.
Yep.
Should we need a huge measurement device? If that's true, where we use these assumptions?
Yeah, good question. So you don't need a huge measurement device. You can do a measurement with just a single qubit. If you've done a measurement with a single qubit, then you could still hope, in principle, to bring that qubit that did the measurement back with your original qubit, interact them again with some unitary, and sort of undo the measurement. Okay, and so it wouldn't make sense to use the measurement postulate at that point, because like if you then do this unitary that undoes the measurement, then you'll get the wrong answer if you'd applied the measurement postulate first. So the only time you can like get away with using the measurement postulate and just rather than doing the full unitary evolution is if the measurement device that measured the thing is so big that there's just no way to like control it well enough to undo that measurement. Or maybe that the measurement outcome got copied into like, some qubits that described the measurement outcome like escaped off to infinity and you have no way of getting them back. At that point, you can just say that the system has irreversibly decohered. There's nothing you can do to undo the decoherence, and just it's fundamentally in a mixed state from your point of view. So that's where the size of the measurement device comes in. But in terms of the formalism, no, it can just be any size you like. It just needs enough states to encode all the different measurement outcomes. Is that clear?
Yes, thank you.
Awesome. Any other questions?
Thank you.
Okay, awesome, guys. I'll see you all on Thursday.